Law or rule of exponents, a to the b raised to the c is a to the b times c, and we should understand why this is the case. But right now we want to apply it to an expression like 1.02 to the 4t. So what do we get if we apply this rule to this? Well, this is a times 4t, which is a b times c. That would be a to the b, which would be a to the fourth, to the c, which would be t. So we could write this as 1.02 to the fourth raised to the t. We could also write it as 1.02 to the t raised to the fourth, but we don't generally use that, so I'm just going to kind of smear that out. Okay? Okay, so if we have a principal function, p naught times 1.02 to the 4t, that's the same as p naught times 1.02 to the fourth to the t, which is the same as p naught times, well, 1.02 to the fourth is 1.0824. Approximately. There are more significant figures out there, but it's approximately 1.0824 raised to the t, meaning, well, this is what you would get if you had an interest rate of 8.24% and did straight interest without compounding. So hopefully we understand that, so that the 2%, okay, this function here represents 8% compounded 4 times a year, compounded quarterly. And that then is the same as getting 8.24% compounded annually. So you're kind of boosting your interest rate from 8% to 8.24% by compounding it quarterly. And of course, we understand from everything we've done before why this stands for quarterly compounding, because we have the 4t, 4 times a year, and we've divided our interest rate by 4 to get the 0.02. So our interest rate must have been 0.08. Okay, well, what if we compound $5,000 at 6% compounding monthly? What do we get? Well, our initial principal is 5,000, so we're going to write that down. And then we're going to have what? 1 plus 1/12 of our 6%. And then we're going to compound that 12 times every year, so we're going to have an exponent of 12t. Now, we've done thorough explanations of why all this works, and if you don't understand this, you want to review. And then that equals then 1.005 raised to the 12t. That's a little bunched up, but it says 1.005, 0.06 divided by 12 is 0.005. And then to the same exponent to the 12t. But then using this, that's 1.005 to the 12th raised to the t. And 1.005 to the 12th, I estimated it was about 1.062. And I said, no, compared to this, it should be a little higher. And I boosted it all the way up to 1.0064. And then somebody said, no, it's 1.0061. Well, it turned out that it had another significant figure. And it rounded off to my original estimate, 1.0062. However, the lesson is rely on your calculator, not on my mental calculations. Okay. And that wasn't even really a mental calculation. That was an intuitive type thing on my part. Not very reliable. Okay, well, anyhow, we understand then that compounding 6% monthly is the same as compounding about 6.2% annually. Okay, now another thing that's kind of new here. We've made passing reference to it, but in the limit, as the number of times you compound in a year approaches infinity, your principal function becomes p of t equals p naught times e to the rt. Okay, the limiting value, for example, 6%, as you go more and more and more times, you divide the 6% by bigger and bigger numbers, giving you a smaller and smaller number after the 1 here, but you're compounding it many times, so you have a lot of, you have a big number times t. Okay, well, because of the way that behaves, and in terms of the definition of E, we can do some rearrangement and get that, and we really should be able to do that within this course, but we haven't been able to. We can establish that this is the case. Now, For $5,000 at 6% compounded continuously then, what's our principal function? Well, principal function, well, R is going to be 6%, which is 0.06. So R is going to be 0.06 and P naught is going to be our initial principal. $5,000 at 6% is going to then be $5,000 for initial principal times e to the 0.06 t. Now, for comparison, that's $5,000 times e to the 0.06 raised to the t, and e to the 0.06 is about 1.0618. Okay, now, this number over here was actually really something like 1.0616, and it rounded up to 0.0062. This also rounds up to 1.062, but it's a little higher than this one. But what you can see is the effective interest rate goes from 6.16% if you compound monthly to only 6.18%, about an extra 0.02% if you go to continuous compounding. So continuous compounding isn't that much of an advantage over monthly compounding. Still, take it if you can get it. Okay, well, there are a couple of applications that we'll talk about.